Iaroslav Gorbachev. Application of deep learning techniques for Stokes investigations using Eddington approximation based on RIS data. So,
thank you. Thank you very much for the introduction. Yes, greetings from Freiburg Science Data Center. Our ultimate goal is to improve today's techniques for the inversion problem. In principle, we are building up the data center. So I've just shown in the very end some links, and you can you're always welcome to visit us. And in principle, in our database, we already have some products, some high-level data products. And this inversion was done in the framework of Mill-Eddington approximation. Of course, it's very simple. It's not stratified atmosphere, but it's a very good test. I mean, it's very good, point where we can test some different models of machine learning techniques. I'm working on this project since December 2022, so in principle 3-4 months, and this is mostly like preliminary results, but I think still interesting to look at it. So as a very first step, I decided by myself to look and to work with a fully connected neural networks, as we heard today a lot about it. And in principle, in general speaking, I will speak, when we speak about the convolutional neural networks, we speak about the classification problems. So here I try to apply the machine learning approach for the regression problems. In principle, for the fully connected neural network, like if we speak about the architecture, it's kind of encoder, classic architecture, and so here, in principle, what I did, we used as an input for our neural networks the Stokes vector IQ UV, and for the output vectors we used so in principle magnetic fields, then azimuth inclinations, and sign of light velocity. So in principle, sign of light velocity, magnetic fields, inclination, and azimuths. And in principle, the point is that for the fully connected neural networks, it works in principle very similar to the classical inversion techniques. So pixel by pixel, you are able to train your neural networks, and I said you map it to the output parameters. But these parameters comes from very fast inversion.
Excuse me, we're running a little bit ahead, so take your time.
Exactly. So in principle, you can see that the results are, I mean, the correlations, when you look at the predictions, which we get, looks very, very good. But at some point, there are some issues with that. So in principle, there are some spreading of the results, especially for the azimuth. And therefore, I tried, my final idea was move to the two-dimensional, to the convolutional neural networks, to the really two-dimensional convolutional neural networks. And in principle, what you can see here are some predictions which looks, so basically our database consists several FITS files. So FITS files corresponds to one single slit positions. If you combine all slits files, you get all full observations. So in principle, so you can see how for instance, the predicted parameters looks as a function of for instance, y coordinates. But in principle, we are able to synthesize the whole spatial maps in the ends. So and here on my last slide, this is like test slides which I would like to present. So we split our data set in 60, 30, 10, like 10% for the test, and basically we try to. This is results you can see that they come from the test data set, and at some point for the velocity and field we got, I think, pretty much very good. I mean, we increased our prediction rate. I mean, our accuracy. But there are some still points for the azimuth and inclination. So I would probably not discuss so much, like you can come to me and to my poster, how we prepared our Stokes vector, because it's pretty much a bit more tiny. For instance, you have to keep in mind that the U, Q, and V component of vectors will be not neglected in comparison to the U, I component. It's very often the case for the sunspots, and therefore you have to make this normalization pretty much in clever way. So basically, I would say. And in the very end, yes, this is kind of outreach, our web, so the link to our database, and Yes, thank you very much for your attention.
Thank you. Questions, please. So we don't have online questions as well. Thank you so much again.